This happens to be FPO. We have several. Looking at it, and then using RF communications, sending that information back to Earth. Well, that also takes 8 minutes. Even though it's RF communications, we're talking about light. Those are just two different frequencies, the same electromagnetic spectrum, right? So rule of the road, speed of light, Einstein, it's going to take the same amount, right? So just to keep that in the back of your mind, because that has enormous implications when we go farther out beyond the sun. The sun's fairly close. In fact, we unitize that. The distance between the sun and the Earth, we call that 1 astronomical unit. We're not in a perfectly circular orbit, but for most cases, you can approximate it that way, and that's 1 AU. And we kind of measure everything else in the solar system against that standard. So that standard of 1 AU is about 8 minutes of communication time. All right. Now, let's move a lot farther out from our sun. Let's go out one planet to Mars. And look how small the sun has now gotten. And here's a beautiful picture, in fact, a video of the sunset from the hills of Mars from one of our rovers. Of course, it's blue. Anyone know why the sunset is blue in Mars? Any guesses? Anyone seen blue sunsets here on Earth? Yes, sir. Right, the composition of the atmosphere is different, so the scattering is different in the atmosphere. So we get blue sunsets there. When we get sunsets, not always. There's a lot of dust storms in Mars, so no sunsets on those days. In fact, dust storms last for months on end. More recently, of course, we've got our two largest rovers that we've ever deployed, starting with Curiosity, and then you can think of it as a sister rover because the locomotion's the same, only the instruments are different. But the Perseverance rover, these were the downward-facing cameras on the bottom of those rovers as they descended upon the surface of the planet, nutating around. They're hanging from the bridle parachute. Very complicated deployment mechanism, but great video. Now, we could not get this video back at the time. It took us a few weeks to communicate each of the frames of these videos back to Earth because the communication rates are so low between planets. And I think I don't have it here. I should show some rates here soon. Okay, let's go even farther away from our sun. So the first of the Jovian planets, Jupiter. This is a mission that's still active right now called Juno. Very interesting mission. And this is some imagery from Juno as it's in orbit around Jupiter. You've all seen Jupiter. You've all seen the large storm on Jupiter. It's like a 1,000-year-old rotational red storm, larger than the Earth itself. But Juno's the first time we've been able to get high-definition imagery of the gases. And you can see, with color correction on this, how many storms there are throughout the planet that, again, we could not see this resolution from our ground-based telescopes. This would be basically the equator of Jupiter right here. And you can see there's like a periodic structure of the storms all throughout the equator. Painting the way that the upper atmosphere of the planet is mixing together. So this would be the North Pole of the planet. So look this up. Juno's a very interesting mission. It's what we call a citizen science mission. You vote on what we're going to take a picture of at Jupiter. You can go into Juno's website and determine, come up with an idea, and then I'll vote on the idea of what to look at. This is probably the worst environment in the entire solar system, other than being inside the sun, from an electronics perspective. Radiation, because of the gravity at Jupiter, is so immense, we have to put everything electrical into a vault in Juno. So the camera's kind of outside, but all the processing, electronics, power management, and that are inside that vault. And we're very limited in terms of data, because there's just not good, even though it's in a vault, there's still radiation going through it. We just reduce it. So the best we can do from storage is about 40 megabytes of storage on board. So we take 40 megabytes of images, depending upon the resolution, and that can be 10 to 100 images. We have to transmit all that back to the ground, empty that out. It's a first in, first out that way. So we have to throttle how much science we can do because of that limitation of the onboard storage. Here's another mission that many people don't know about. Should. Cassini, or a portion of Cassini, landed on the moon of Saturn. That lander was called Huygens, and it landed on Titan. Very interesting moon, one of the most interesting moons in the solar system. That's a touchdown of that. If you go up on YouTube, you can watch the full descent through an upper cloud deck. It goes between a couple mountain peaks. It's phenomenal. It's about 20 minutes long. I highly encourage you to watch it. So Cassini was an orbiter, but when it dropped Huygens, so Huygens had that imagery, and it was relaying all of those messages up through Cassini and then back towards Earth. So for a short duration of time, Cassini was a communications relay satellite in addition to being a scientific orbiter. Hopefully we'll be able to get back to Titan. The subterranean seas in Titan, there's some thought that there's life in those seas. So one thing we're doing conceptually now is trying to figure out what would a submarine look like that could be deployed in that ocean. And it's not water in that ocean. It's got a lot of metal in it. So how do you get an RF signal down to a submarine in a conductive fluid so that you could try to get some telemetry back from the submarine? Very interesting problem that we're working on right now. New Horizons. So this was our first time actually getting to Pluto, and it was a single flyby. Very aggressive mission in terms of its profile. Did not take long to get there. It was only going to fly by once. So we had one pass to expose all the images. And it took, even though that was a single flyby, it took a long time, basically about a year, to transmit all those images back. You know, if you went to the library before this mission and you tried to find a book on Pluto, very little. You wouldn't find a book on Pluto because we just didn't know. Ever since Pluto was discovered, we knew where to look for it in the sky to find it, and you could point your telescope there. If you had a big enough telescope, you could take a picture of it, but we knew nothing about the internal, structure of the planet, what the surface features were, what the composition might be. And now there'll be many books written on Pluto because of this single mission, and hopefully we'll be able to land on there in the future. But I want you to notice the data rate, 2 kilobits per second. Hopefully none of you have internet speed that slow, but that's the reason why it took so long to get each of those images back. And I'll just mention, by the way, when you're communicating with a spacecraft like New Horizons or any spacecraft in deep space, you really only get a duration of about 40, 45 minutes per day on average to communicate with them. There's so many out there. There's about 100 right now, if you refer back to that previous slide that I showed, throughout the solar system. And we don't have 100 telescopes on the ground, radio telescopes to talk to everybody. So we have to share time. We talk to one, get some imagery, get some data, send some commands, and we move over and we talk to another one, and we talk to another one, all in a pre-scheduled, kind of a manual manner. Keep that thought in mind, and we'll return. So I mentioned that we use RF to communicate with our satellites right now, specifically the microwave regime. And there's a few different bands that we use in there, typically starting at around 2 gigahertz, and we'll go up to about the 30 gigahertz regime. We break those up into letter designations. We call the lower frequencies S band, that's about 2 to 4 gigahertz, and then we go into something called X band, goes a little higher, and then A band is the top end of that. But we do a lot of other things while we're communicating. We help the satellite navigate. So these are some very simple, oh, by the way, because we're using electromagnetic radiation to pass information back and forth with our carrier wave, we certainly have to point our ground-based antenna at the satellite. Well, our antenna has encoders in it for up and down and left and right, so we call that azimuth and elevation. So we can read the values of those encoders, which are fairly precise, and we can let the satellite know where it is in relation to that antenna, because the satellite never knows exactly where it's at. It's somewhat lost in space. We're always somewhat lost throughout our day, right? you're never truly lost. You should always know what country you're in, I hope, and you should know what city you're in. But as you're driving around, you might get a little lost. You might not know what road you're on, but you know what city you're in, you know what state you're in, you know what country you're in. Same thing with spacecraft. So between the last time we talked to the spacecraft and then today we set up a communications link, it's drifted a little bit. And we can measure that drift from the ground. And while we're transmitting information back and forth, we include, hey, by the way, our antenna is pointed a little this way, which means that you moved over to here. Here's where you're at. Please update your knowledge of where you're at. Technical term for that is TLE, two-line element. The satellite always keeps track of where it's at in this TLE set on board. That's important. If it has a camera and it's trying to do some work over here locally, it needs to know where it is in a parent coordinate system. So we help that by giving it tracking. Ranging's even easier. All we simply do is send out a pulse, and then that pulse returns. We divide by 2, look at the speed of light, and because we're in the microwave regime, that can give us, on average, about a 1 meter resolution of the range of the satellite down to a ground terminal. Now, again, when we first set up the link, we make some of these radiometric measurements to determine where the spacecraft is at, how far it is away from us, and then we let it know so it can update its local information, because there's no GPS out there in deep space. And then very finally, what we'll do is we'll look at some Doppler. So has everyone heard of Doppler before? Show of hands. Okay, so same as an audio Doppler, right? We have the red shift and the blue shift, whether the 2 points are moving towards or away from each other. We have this agreed upon communication structure where when we communicate with the satellite, it is going to have a very narrow, very specific carrier frequency. So if it's an S-band satellite, we know S-band is like 2 gigahertz to 4 gigahertz. By the mission, you'll be assigned 3.194 gigahertz and nothing else. You're never allowed to radiate outside of that, and that's what gets built and flown on the spacecraft. But of course, it's moving, right, in relation to us. So when that 3.195, I hope that's what I said, gigahertz comes down, we are going to see an apparent shift of that carrier frequency based on the Doppler. We'll measure that, and again, we'll then let the satellite know, here is your relative range rate. So lastly, we do the tracking, we do the ranging, and we do the Doppler measurements. And I'll just mention lastly a very special thing that we'll do. Every once in a while, because the Earth is rotating, we have antennas internationally across the world. Every once in a while, 2 of our antennas become in view with the spacecraft. And then when that happens, we can do something even better, which is called very long baseline interferometry. We essentially set up a triangle here where, let's say we have Canberra, Australia. That's where we have some antennas over here. We have Goldstone, California. We know exactly how far those 2 antennas are from each other. That's been characterized over half of a century. We can have atomic clocks here to know exactly what time it is. Same atomic clock running over here in sync. So now when the spacecraft talks back to us, we're going to have a path length difference between both of these arms of an interferometer. We've basically sent up a solar system baseline interferometer. So the time delay of this message to that message can be accurately compared with each other. And so even better than just reading off the encoders on board one ground station, we can do a lot better, in fact, and get us down into the nanoradian regime where that spacecraft is posed in 3D space. It's not always necessary. We don't do it for every spacecraft. But if you're going to do something like land on a planet, go through the upper atmosphere, you have to be at just the right critical angle for your heat shield. We'll do a lot of these VLBI measurements right before those maneuvers are done to really dial in the local knowledge, because we might have to revisit. Okay, I mentioned we don't have 100 antennas out there, but we do have a lot. Here's where they all are at. So you can see on every continent we have ground terminals. You imagine the Earth is rotating, so we have to keep hopping from terminal to terminal as they become in view with the different spacecraft throughout the solar system on the ecliptic plane. If you're interested in learning more about this, and I'll give you this presentation afterward. These are active links you can click on. There's a nice model of the entire space network in 3D. It's called the 3D demo. And you can go through there and kind of zoom your camera around the solar system and around Earth up here to kind of see those links. And then there's an interactive game here that shows you some of the challenges of setting up a communications link. So you can choose to be a manager or a scientist or an engineer with a new mission design. Using these assets, what are some of the trade-offs that you have to make, the decisions that you have to make in order to get the data back? I just want to mention that as an aside. So I've been mentioning some of the missions. Here's the actual performance rates. Mars Reconnaissance Orbiter is still out circling the planet. Most of the very good imagery that you might have seen of the surface of Mars comes from MRO. It has a big camera on board. And Mars takes about 2 years to go around the sun. Of course, it takes us 1 year to go around the sun. So what that means is that every 2 years, Earth and Mars are together next to each other on one side of the sun. And then a little bit later, we're at completely opposite sides of the sun. So what that means is that the distance between Earth and Mars vary wildly. In fact, when we're close, that's when you would launch to go to Mars. And you got to wait 2 years, and then we're close again, and you would like bring humans back for a human mission. So that's why you see this round trip light time varying so much. When the planet is very close to Earth, it's about 8 minutes. Send a message and bring it back. And then, of course, the bad time of the year at apogee, it can take almost an hour, 54 minutes. Something like Hubble, right, that is very close to the Earth. So we have a fraction of a second of delay, 0.36 seconds. That's an older spacecraft. It does use an older communication system. So that one tops out at 4 kilobits per second. MRO being much newer, even though it's farther out, goes faster, but it still only tops out at 4 megabits per second. So you can imagine taking images, the kind of images like I showed you previously are on the order of sometimes a gigabyte, 100 gigabytes large. They're scientific images. So it can take weeks to bring some of those back if you're only talking, let's say, an hour a day at these kinds of rates. Very, very slow. Of course, the rates go down the further out in the solar system. Cassini down here in the 10s to 100 kilobits per second, and oh, by the way, the time of light delay, again, depending on orbital dynamics, could be anywhere between 2 to 3 hours. Heliophysics mission, stereo. Stereo is actually 2 spacecraft circumnavigating the sun, and we get an average because, again, time is kind of changing there with distance of around 20 minutes from that. If you go to Voyager, Voyager 1, Voyager 2, we're talking about well over 30 hours. So imagine from a cadence perspective, imagine you're an operator on a team sending commands to one of these spacecrafts. Let's say it's Voyager. You want Voyager to do something, reset a circuit breaker, take flux measurement off this instrument. Well, you assemble that message and compile it and send it up, and it's going to take 15 to 17 hours to get there. And so you're going to go home and go to bed and wake up the next morning and still not have anything. And it's going to hopefully do what you needed it to do correctly. It's not always true, but hopefully. And then 15 more or 17 more hours back, it sends a response back to you. Yes, I was able to follow your instruction, or I tried and something failed. So the cadence of spacecraft communications, operations, navigation, very, very slow, because of that. You have to pre-plan in advance everything you'd like to do. We can't just tell the rover to turn left now, immediately, right? Okay. The types of data now, let's talk into what we're actually sending. I've shared a lot of neat pictures with you, but there's a lot more that we're exchanging with the spacecraft. And in fact, the most important information, the lowest bit information, which is tracking, telemetry, and control. So that is some of those radiometric measurements that I mentioned earlier, letting the spacecraft know where it's at, but also controlling the spacecraft. Turn a little this way, turn a little that way, turn the heater on, reset a circuit breaker. So this is the highest information. That's the proper care and feeding of the spacecraft. And then, of course, we have why we have the spacecraft out there in the first place, this getting the scientific data from the instrumentation, which could be pictures, video, plasma measurements. And then if it's of course, if it's a human-rated mission, then we've got all the biometrics there as well. So very different kinds of information, some big, some small, some high priority, some low priority. If you take a picture and you don't get it back for a few weeks, that might not be a problem at all. But if one of your onboard memory storage elements get hit by radiation and comes offline, you want to know that immediately. So that would be part of the TT&C up here. In short, what we wish we could have is uninterrupted data from anywhere in the solar system. So talk to everybody at the same time without any connections at infinite data rates. That would be amazing, especially for human exploration. And a good quality of service that you and I enjoy with our TCP/IP-based networking protocols, right? So we can have things like reliable networks and networks. We can have secure networks. A lot of these concepts break apart because of that time delay and that varying time delay. Despite that, here's kind of where we're at from a state of practice. So we started this endeavor, as I mentioned, in the S-band microwave regime in 1960, coming from R&D. A lot of that R&D was made in World War II, so leveraging World War II radar technologies for spacecraft. And soon after, topping that out from a bandwidth perspective, hopping over to a higher carrier frequency, 8 to 12 gigahertz. This is what we primarily lean on today, X-band. We're migrating in a Ka band, which gives us even higher data rates. And then finally, what I want to talk about here is the optical regime, which we consider 1550 nanometers to be our standard. Notice that we jumped from frequency, gigahertz, to wavelength in nanometers. It's a convention. When you talk about optics, it's a lot easier to talk about the particular wavelength than the frequency. But of course, it's just a reciprocal relationship. Usually, that's the standard. So this is my particular area, which is laser communications. And as you could understand, probably intuitively, going to a higher carrier frequency, we should be able to pack more information onto that carrier wave, and that is true. Typically, and it'll vary on mission to mission, we can see 1, 2 orders of magnitude improvement. On average, a 20-fold increase would be fair to claim in data rate by going to laser over microwave. But again, there's a lot of variables with that. It's not truly an apples-to-apples comparison. But I'll tell you, what's much more attractive isn't the performance, but the fact that, remember when I mentioned if you're going to fly a mission, you only get a single frequency to communicate at, and then you'll get another one to communicate back with. There's actually a pair. We call that the return link and the forward link. So each mission needs at least 2 RF frequencies. We're running out. There's a finite amount of frequencies, and those frequencies are internationally agreed upon in Geneva. You've heard of the FCC, right? Federal Communications. So bigger than them, we have what's known as the NTIA, which meets in Geneva, and all countries get their frequency allocations. Your cell phone in your pocket had to go through that process to be allocated to use those frequencies to communicate. Spacecraft are no different. We only have, an S-band, 2 to 4 gigahertz. That is full. And X-band is full as well because we've got radar systems and communication systems both competing in that range. So the more missions that you want to fly, there's no more frequencies in the RF domain to go to, at least in those bands. Ka is coming, and that's great. It's basically here now. But we know that everyone's going to jump on it and get all that wrapped up and allocated. We've got people like Elon Musk out there and other private companies. A lot of satellites that are going to use up a lot of that bandwidth. We're in contention with them. Completely unregulated in the laser regime. There is no regulation. So that's one of the key concepts of why the jump to laser is good. because we don't go through all that legal time, which can take years to do before the mission even flies. You have to pay for it and monitor it. So just want to mention that because it's not intuitive. People think about engineers like myself, we all want better performance, and that's true, but the legal implication here is almost stronger of making that case. You can have smaller and lighter weight systems, and I'll show you examples of that, but what I really want to show you here in this picture is that if you had a future generation Ka-band system and on an orbiter around Mars, and you wanted to generate a Google Earth repository of data of Mars, so basically 1 meter per pixel resolution of the entire planet, and you could have it on your desktop computer and spin it around virtually, that'd be amazing. If we could do that with a Ka-band system, it would take about 2 years to get all that information back to Earth. With a laser-based system, we could do it in about 2 months. So to give you kind of a overall integration over time of what the payoff is. And then the last thing I'll mention, in space we take a lot of scientific RF measurements. Almost all of our spacecraft have additional antennas on them that are not there for communication. Measuring plasmas, was one. The problem is if you have a high power communications RF system right next to a very sensitive, low power scientific instrument, also RF, you can't run both at the same time. So you collect a little science and then you shut down the listening station and activate the communication system. Because optical is so far away, RF regime, we can have sensitive RF and a laser-based communication system, and they will not interfere with each other. So we can take our measurements and communicate them real time back to Earth at the same time. Again, something that isn't so intuitive, and that's why I wanted to just kind of mention it here, because it's not all about performance. Okay, I mentioned to you that you might assume that going to a higher frequency allows us to put more information on a carrier wave, and that is true. But there's a whole different way to explain it, which I think might be better, and I'll share that with you here. Kind of a thought experiment. Anyone familiar with the geo belt? Geosynchronous orbit, a few? So imagine a hula hoop around the Earth at the equator. That's 35,000 kilometers out. And many countries, including the United States, this is where we populate our telecommunications satellites. It's way out there, right? We don't send humans to geo. It takes a lot of TV to get out to geo, but our combirds are all out there. So imagine we flew a telecommunications satellite out to geo, which we've done many, and it has an RF dish 1 meter in diameter. And we're going to aim that satellite down on Cleveland, Ohio, where I'm from, and that dish, and let's say we use a Ka-band system, so we're up at 30 gigahertz, so we have a very good RF system. Diffraction limited will give us a spot size of radiation that encircles this 300-mile footprint. And so what I want you to notice here is Cleveland is right here in the center, Toledo's over here. That means that Cleveland and Toledo can receive that signal easily or within the footprint of the RF encircled energy. That's great, and what's even better is the satellite doesn't have to have a good pointing and control system. It could be off by fractions of a degree, and that circle is going to move around, but Cleveland and Toledo will still be in the middle of it. We can still talk. So it relaxes control system requirements on the spacecraft. That's wonderful. The bad part is we're putting all that RF energy everywhere other than where we need it. We've got an antenna maybe in Cleveland, we've got an antenna in Toledo, and then we're lighting up all of Lake Erie with RF energy where it doesn't need to be. Here's the problem with that. If I started whispering right now, I'd have to slow down my talking. Right? Talk quiet to talk slower because the signal noise ratio is getting worse. I talk louder, a lot faster, and you can hear what I'm doing because the signal to noise ratio is greater. So the signal to noise ratio is not so good with this because we're putting all the signal everywhere else but where the particular receiver is at. So we have to talk slower. Make sense? It's a geometrical problem. It's also a bandwidth problem. They're related. the pointing and the tracking and the aperture, all this is related. Now, take the exact same satellite, and we're going to fly an optical telescope, a very small one, 10 centimeters in diameter. So that's one change. The other change is optical. We're going to fly at 1550 nanometer or 1.55 micron. Now our footprint, well, it's smaller than Cleveland, and it's smaller than Brook Park, and it's even smaller than Hopkins Airport right here. If you're familiar with airport, here's 480, and here's 71, where they cross. And that's NASA right here, this triangle. So that footprint is even smaller than NASA. So now all that energy is much, much more collimated. So the signal goes way up. So I can talk a lot faster. This is why you can communicate so faster with a laser than with RF. And you could say the same about a higher frequency RF than a lower frequency. If I jump to something beyond Ka-band, start to break that down as well. Okay, that's great. And also it's great for privacy. Those of you that are in security studies, and we were looking at key encryption schemes. That's great. This is physical layer security. A spy could go down the river here, put in a telescope, and they wouldn't, they wouldn't be able to intercept that. They have to physically be on campus looking up in order to receive the signal to even try to intercept it. So, physical layer security isn't the be-all end-all, but it does give you that if you care about that. Now here's the problem. Very challenging pointing control. This entire beam, the RF beam was 300 miles wide. Now we're 600 meters wide, which means if our satellite is vibrating, it's moving around, why would a satellite vibrate? Why would it shake and vibrate and move around? They all do. What? Yeah, that's one. If a thruster fires, so imagine a step function of a valve opening and some hydrazine or something comes out one side, it's going to move over, it's going to vibrate the whole thing. Right, but let's say we're not even doing that. We're just sitting there. Solar wind, we push it around, which we would thrust against every once in a while. We call it station keeping. You get blown off a little bit, and then every once in a while you got to come back. But let's say when you're quiescent, why would you be vibrating? Any thoughts? I'm trying to give you a visual. Solar panels, if we have solar panels, if we're close enough to the sun to have them, imagine the thermal deformation of those solar panels, because half is always in the sun and the other half is always in the shade, and that's always changing. They're fluttering like a butterfly, shaking the entire satellite. Now, if you don't have solar panels, you still have other noisy mechanical components, reaction wheels. Many of our satellites don't have thrusters. Some of them do, some of them don't. Many have counter-rotating wheels at about 3,000 RPM, a pair for each axis of the satellite. So if you de-spin one of those wheels a little bit, a conservation of momentum, that starts to move the satellite around, and then you spin it back up again. Well, having those wheels spinning is constantly shaking the satellite. I mention these things because these are all things that are going to prevent us from holding a pencil beam of laser down on a point which is the Earth, ultimately, right? And many systems can't handle that, so we have to do a little better. And then finally, I'll mention, especially for Cleveland, Ohio, the reason NASA is in Cleveland, Ohio is because of cloud coverage, because prior to NASA, it was NACA, and they knew that if we got somewhere where it was really cloudy, people would be able to spy on us during World War II, during our advanced aircraft work that we were doing. Unfortunately, if I put an optical ground terminal in Cleveland, it's going to be covered in clouds, and we won't be able to penetrate through that. RF has no problem. K-band starts to a little bit have a problem with precipitation and aerosols, but X-band goes, right? In fact, we use X-band for seeing clouds. Perfect at that wave. Okay, so I just want to paint a fair picture there. RF is not going away. It's wonderful. Think of optical as another tool in your toolbox for emission. I added a little chart here because I use the word microradian. How many of you work in microradians? That's what I expected. I didn't either until I got optical communications. It's really hard to be a human and think about what a microradian is. So I put together this to kind of show you that. If you look up at the sun or the moon from the surface of our planet. Imagine a protractor in your eyeball looking at the angle that those bodies represent. We're in the milliradian. You can measure the distance across either the single-digit milliradians. If you were to look at a penny at 4 kilometers, you start to get into the hundreds of microradians. This is interesting. Who's seen Jupiter? Looked up and seen Jupiter at night. Anyone looked at Jupiter? It's pretty bright. Nobody? Few people. Okay. You can definitely see it with a telescope, but if you know where to look, you can see Jupiter. You're actually not seeing the planet. It's too small to see with the naked eye, but you're seeing the halo of the light bouncing off of Jupiter and then being even widened up from our own atmosphere. But if you got it, you don't need a good telescope, a very low diameter telescope, looked at Jupiter and measured on your reticle, you'd see it's 145 microradians in diameter. To Neptune, which you definitely can't see with the naked eye, but you can see with the telescope, now we're in a single-digit microradian. So that's kind of where our communications beams are. We're talking about looking at Neptune from Earth. Pluto then gets us another order of magnitude down here. So here's how the pointing challenge is solved. We basically build an artificial star. You can think of it that way, where the transmitter and the receiver project a wider laser beam at each other. And remember, I mentioned you're never completely lost in space. So today at noon, I want to talk to my spacecraft. And I don't know exactly where it is, but I know it should at least be over there in the sky. So I turn on a very wide laser beam, and I start doing a spiral scan or a raster scan, some pre-programmed open-loop scan of that quadrant of the sky. Spacecraft is doing the same thing because our clocks are synchronized, and it tries to find the ground terminal. Eventually, we light each other up. And we know we do because we have detectors that are looking for 1550 nanometers at our beacon frequency. So we call that acquisition, where we've basically bore-sighted each other's telescopes towards each other. We're not perfectly aligned, but we at least see each other. Then it gets a lot easier. Then we go into a tracking mechanism where we can progressively narrow up our beam. That increases our signal-to-noise ratio and also centroid on each other so that we're in a handshaked relationship. And now we can start sending command and control information back. Hey, move a little right, move a little left. And eventually we've established our link. That whole process takes 5-10 seconds at most. It's a very, very fast automated process. And I'll show you some of the equipment behind. Beginning to end, this is what an optical communication system looks like. So up on the spacecraft, although you can imagine the inverse is true going the other way, we have an amplifier over here. So for the RF domain, we would have a solid-state power amplifier or a traveling wave tube amplifier. Here we have a laser fiber amplifier. The exact same amplifiers that are at the bottom of the Atlantic and the Pacific Ocean that connect our entire World Wide Web together. We're using that same technology because it's very robust. Then we have an optical modem. So this is where you impart the message to the carrier wave. We have to have some fine mirrors. So these are the mirrors that are used to get you that last little bit of microradians. We also need a way to do coarse pointing. So we'll have a coarse pointing gimbal around a telescope, which is our transmit optics. And then because we have always noisy spacecraft, mechanically noisy, thermally noisy, we have to have a vibration isolation platform right here that all of this stuff rides on top of. Then our laser goes all the way through space, hopefully not through some bad atmosphere, hopefully goes through some cloud-free line of sight back to Earth, intersect with one or several telescope arrays, and then finally impinge on detectors, which I'm showing right there are some nanowire detectors I can show you some detail of. So there's a lot here, some old technology, some new technology. I'll drive you through a few of the interesting things that we've been working on. So here's MRO again, and MRO was interesting because we flew a bunch of accelerometers on board that spacecraft, and it's still operating right now, so we're always getting accelerometer data. This is what the shaking of MRO looks like in the time domain from those accelerometers. You can see it shaking, and something obviously happened, you know, right there. Perhaps it came on the back of the planet and the sun hit it, And it started flapping its wings, because that actually does have solar panels and reaction wheels on board. So here's our time domain representation. Now, as engineers, that doesn't really mean a whole lot to us. It doesn't give you intuition about how it's shaking around. So we can look at things in the frequency domain. So we're familiar with that, taking the Fourier transform of a time domain signal. We look at that same information in the frequency domain, and this is, in fact, what it looks like. And this is very meaningful to us. We can see that an MRO spacecraft has very constant disturbances from low frequency up to one particular break frequency. And this is one particular axis. There'll be a little different axis to axis, and then rolls off like a low-pass filter, like many mechanical systems act like a low-pass filter. So we know if we want to get rid of these vibrations, we have to develop a vibration isolation platform which will reduce all of the energy, about 30 to 50 decibels down. Suppress all of these frequencies. After we don't have to anymore because the spacecraft is naturally damping those out. That's what you see here on the right here. So that's a prototype. It's a hybrid active-passive platform. It has some passive coils in it, just like suspension on your car. And it has some active electronics in it that's also got actuators that's taking up some of the higher energy resonances out of the spacecraft. So this is what a quiescent platform looks like. So the fun part is then testing it. So you have to mount that to a vibration platform and shake it around to that profile and put accelerometers on top, and we definitely shouldn't see that when we're done as engineers. Going for a ride on top of that platform is the gimbal. This is how we're going to move our telescope independently of the spacecraft. This is a prototype of that gimbal called a Canfield joint that we put together. This gives us what we call a hemispherical field of regard. All that means is that you can point within half of a hemisphere anywhere. So the spacecraft, you generally want pointed down towards the planetary surface, taking measurements. And you want to be able to point your antenna or your optical communication system independently of that around an entire hemisphere. This will allow that to happen. Kind of an interesting design. It was the mathematics were put together by a gentleman named Stephen Canfield many years ago, a mathematician, and we found his equations, and it took us a while to figure out how to get that to something electrical and mechanical constructed, and then of course the closed control system to make it work. But there's the prototype for that. I'll mention another interesting thing that we've been working on. Like I said, RF is not going away, and it never should. It's very, very good for certain things. This idea of putting the two together, how would you have RF and optical on a spacecraft at the same time? So this would be an RF telescope and an optical telescope together. We call that a teletenna. I guess it sounds better than antiscope, I hope. But what you're seeing is a mesh-based Ka-band reflector. It's about 3 meters diameter, and then nested on the inside of that is an optical telescope. So when you point one, you automatically point the other, and we can enjoy the benefit of both. Maybe there's cloud coverage, and so you turn on the Ka-band system, and then go away. We turn on the optical system. That's something that we're building up now. From a navigation standpoint, when you go out to Mars or beyond, this idea of using an artificial beacon on Earth kind of goes away, right, because of the time delay. At Mars, we're talking about maybe around 20 minutes average. It will vary between 8 and 40 round trip. So we can't be dependent upon Earth letting us know where we're at all the time. We've been looking at star trackers and have been developing a much better, smaller and better fidelity star tracker that you can see up here. But more importantly, the mechanism for trying to figure out where you're at in solving the lost in space problem. This is a fascinating multidisciplinary problem. So we have this physical photonic device known as a star tracker. It's just a camera and a telescope. You take a picture of the sky. Hopefully you take a picture of the sky that has a grouping of stars in it. Imagine that detector that's at the focal plane array of the telescope. It's just pixels, just like your television at home. It has a finite number of pixels. And you have several stars that lit up several of those pixels. Step one is determining exactly where those stars are at. You have a resolution problem here. So imagine you had 4 pixels like this. 1, 2, 3, 4. And I lit up all of them with one star. Where's the star? You kind of have to count. This pixel has so much energy. This one has so much energy. It's called centroiding. It's a classic mathematical problem. Centroiding is an art form in and of itself in art and science, right? So we go through this centroiding algorithm to try to determine where each star is in our star field. Then it's a big data problem, database problem, because I can measure the distance between each of those stars. I have a topology, and I have this enormous memory of all the stars that's out there that I want to search, because I maybe see a portion of a constellation here, and I want to find it and match it, because if the camera sees that, then I should be here, right? But I have to do this in a few clock cycles, because everything's kind of moving around. So we have some database stuff there with pattern recognition. I'll say it's similar to your Social Security number. If you're at a terminal and you type in the first number of your Social Security number, mine's 3. When you type in 3, already I can reduce that database and collapse all the 1s and the 2s and the 4s and the 5s. I'm not even going to search any of that. You type in the next number of your Social Security number, database collapse. Philosophically, we're doing the same thing here, because we don't have time to look through everything, because the spacecraft, again, is moving. Everything's changing. So we get our pattern recognition with the star catalog. We determine what we're looking at down the star camera. And then from there, we can go to classical, I shouldn't say that word, modern controls with Kalman filtering to get our quaternion estimation of where we're at. So now we can find Earth. We can find the point on Earth that we need to communicate with, and we don't need that uplink beacon. So we call that beaconless communications. Let me check my time here and see how I'm doing. Okay, I think we're doing okay. So I mentioned actually I already mentioned that, so let me get to the actual modulation, putting information onto the laser. This happens in the optical modem. Inside the modem, we have a couple things. We have a modulator, which is a crystal device that can change a few different things. We could turn the signal on and off, the amplitude of the signal. We could adjust the phase of the signal. We do that a lot in the RF domain when we communicate. We can do the same in the optical regime. And which way we do this will depend on the mission. The simplest way is to turn the laser on and off. I could use Morse code, right? Or if I was digital, I could say when the laser's on, that's a digital 1, and when it's off, that's a digital 0. And then that's the thing. We call that on-off keying, OOK. All right? It's not very efficient, but it does work, and in fact, it is used. There's something a little bit more crafty I want to share with you that we use in the deep space, and that's called pulse position modulation, PPM. It's a variation of on-off keying, but we're actually able to get many bits encoded onto a single photon from this. And this is interesting. I'm going to take a moment to run you through it. Here's time down here. And we're going to break time into a series of frames. Here's the first frame. Here's the second frame. Here's the third frame. And they're separated by some guard times in between. Each frame has a finite number of slots within it. So here is the lowest order slot and the highest order slot. The way I drew this, I'm showing a 3-ary PPM. So imagine 3 bits, and you can count from 0, 0, 0 all the way up to 1, 1, 1. So in this case, there's all of our slots counting up. So on the spacecraft, I have this buffer of data that I want to read out of my first in, first out memory. And let's say I look at the first chunk, the first 3 bits, and it's a 0, 0, 1. What that means is in time, I only turn the laser on for the second slot of the first frame, and that will correspond to those first 3 bits. And then I go down and I read the next 3 bits. In this case, the next 3 bits are 1, 1, 0. Well, now I have to wait until that slot comes up, and then I pop the laser on and off really fast. And then I read the next 3 bits. This could all be a picture that I'm forming up and transmitting across the laser. So in this way, every time I turn the laser on in that, I'm actually transmitting 3 bits. Now, in actuality, we use a much higher order scheme. We can use 64 area, we can use 128, but I didn't want to draw that because it would be really hard and much more difficult to explain. But here's a 3-area pulse position modulation. The reason this is so good is because the laser's off most of the time. The majority of time, I don't have the laser on, which means that it's the most efficient thing I could have. Again, we're thinking of deep space, maybe beyond a solar panel, so you're running off a radioisotope thermal generator. We have a saying on our lab, every bit that you transmit is a bit closer to death. Okay. It's true. You have a finite amount of power. So you have to be very careful how you transmit these bits. When you're in deep space, efficiency is what we're optimizing around. We're going to give up speed for efficiency, and this is how we'll do it. Now, what will happen after these pulses all the way back to Earth, and especially after they go through those last several miles of the atmosphere, we're actually only going to get single photons back at the detector. 1 photon. We actually count them. Got one. And then we look at it to an atomic clock and figure out where in the frame that corresponds to our slot. These are the rules of the road. We've agreed upon these rules with the spacecraft. We're looking at the same script, right? So timing synchronization is key towards this. Okay, this is our system. In order to do that, we're using standard FPGAs. We like the Xilinx, but anything will do. We're now using some of the ultra scales. It's a little hard to see here, but there's the electronic PPM signal coming off the FPGA. So imagine we're using the FPGA to read some memory and then create electrical pulse train, which is driving the electro-optic modulator, which is opening and closing. You can think of it as physically opening, closing an aperture, but really it's just changing the transmissibility at 1550 nanometers, essentially turning on and off the laser beam. The actual detector, let me forward to that, in a telescope on the ground looks like this. It's a wordful. Cryogenic superconducting nanowire single photon detector. It's a single photon detector because we're looking at getting a single photon back from one of those slot widths. And it's a nanowire because it's a lithography of literally nanowires. We use a couple different chemistries, either niobium niobate or tungsten silicide. Either way, we have to put them in a cryostat around single-digit Kelvin to get them to run. Basically, what we have here is an instrumentation circuit which puts the current through that device, measures the voltage drop. Every time a photon comes in, it causes localized resistive heating, which then changes our circuit over here because it's going to change the amount of current that it's sourcing because the resistance has changed. And that's how we know we just got a photon. Then it has to physically cool off. We call that resetting to its original state. So it does take some time to cool off because we're using the Joule heating concept here, and that's those guard times in between. Okay, and the last technology I want to mention, getting here to the end of the talk, is what I'm really focused on, which is the architecture and networking aspect of not just optical communications, but all space communications. I call this the porcupine chart. Those missions that we're flying right now look like this. They have, for the most part, dedicated links back to Earth. Spacecraft do not communicate with each other. All these rules on frequency and modulation and encoding and security are agreed upon with some Earth-born terminal. And once a day, one of these links will become active to every single one of these spacecraft. It kind of works with 100 spacecraft. It definitely isn't going to work with 200. It does not scale. We have a major scalability problem here because we've got some great launch vehicles about to come online. We're going to get a lot more hardware out to space to investigate our solar system, but we don't have any network topology here. We have a bunch of independent point-to-point links. What we need to do is take the philosophies of our Earth-born internet and have local networks around, say, the moon and Earth and other planets so that we can start relaying information back so we're not talking to everybody once a day for about 40 minutes or so. Easier said than done because this is a very tortuous path. Links are coming and going all the time. A highly disconnected environment, a highly ad hoc environment, and a highly latent environment. All things that TCP-based networking can't help us, unfortunately. Those of you who study, TCP IP and the timeout delays and acknowledgement, any sort of acknowledgement-based networking won't work in space. Everything will just time out. It takes weeks for the message to get back, right? So there's a new, I shouldn't say new because the standard's been around a while, but we're finally rolling it out as an implementation protocol called DTN, delay tolerant networking. Some people refer to it as disruption or disconnection. It's all those things. And it's a standard that you can find called RFC 5050. This is an open standard. We have a working group. Anyone can contribute to this. And we're also working on implementation. So we have software implementations of this. We have a few different hardware implementations using DSPs as well as FPGAs. To get DTN running at about 100 gigabits per second is our goal right now in the lab, 40 or 50 gigabits per second on some ultra-scale FPGAs. But in short, what it does is it takes into account the fact that we have these long latencies. So major disconnections, major latencies, that we have to store data for a longer time than I would on the World Wide Web, and then forward it to a neighbor to eventually get it back to the ground. And I know something about the network, but we don't know everything about that network. And so you can think of this as a very crude implementation of cognition. This is kind of like the basic level, where instead of a person on the ground pulling levers to talk to a spacecraft, we're building an autonomy system to find your neighbor and use them as a relay to help you back home. True cognition would be things like adding network discovery, having routing tables rather than static routing tables that we are pre-selecting as humans, have the network figure out the right way to do that. So the major buzzword, and I would say this even beyond space communications, adding any semblance of cognition to the space environment is the key word today. And if you're interested in working in the space environment, anything you can do to help bring autonomy to our spacecraft will be the most important advancements that we can make within the next 10 or 20 years. Because again, we can't scale beyond 100 spacecraft doing everything manually like we're doing right now. And so, like I mentioned, dynamic routing is one of the main things that we're looking at. But we're also looking at cognitive radios, being able to change from different frequencies, or changing from RF to optical. We let the system determine when to go from one to the other if you have both, rather than, again, a human making that decision. So we try these different methods in the lab. This is kind of what some of our labs look like. So if we have some component technologies, we try to emulate the space network, this network using a bunch of server computers, and try to throw information from one side of the solar system to the other in an emulated environment, and see, how many errors that we get, and quality of service and things of that nature. From a technology development standpoint, the next step is we take our devices, we add them together, build an entire radio, so to speak, and then we have to irradiate it in our electromagnetic interference laboratory. We'll do vibration testing in the vibration laboratory, deep soaks in our environmental chambers, so high vacuum and temperature of the environment that the spacecraft would be in. And then, of course, lastly, in Sandusky, Ohio, we have a large reverberant acoustic test facility. So that basically emulates launch, the reverberation of launch acoustically, kind of like a vibration test, but just for that instantaneous few seconds of surviving launch. And to conclude, I just want to show you some successes that we had in that. A few years ago, we did fly to the moon with a laser communications payload on a orbiter called LOTI, which you see over here. And we're able to communicate at over 600 megabits per second from the moon back to Earth. Magnitude faster than anything RF had done at that time, and the laser wasn't necessarily cutting edge on that. Again, it was a tech demo. But we were able to have multiple channels of high definition video exchange up and back, and then we did bit checks in that, and got very good data back from the LOTI mission. Much more recently, even this year in the fall, we put a laser terminal on one of our NASA aircraft, flew it all over Lake Erie, got 1 gigabit per second across that in a high humidity environment. Flying networking protocol as well, DTN. And here's the upcoming stuff. We just launched a satellite called LCRD, Laser Communications Relay Demonstration. That's out of that GeoBelt. And we're about to put a laser on the International Space Station, which will relay through that at over a gigabit per second. So what you'll be able to do, what I hope we'll all be able to do, is go up on YouTube, and there'll be an ISS channel, and you'll be able to cruise between each of the high-definition cameras on the ISS streaming live, which is something we can't do right now. So we should be able to get many channels of HD video down from that pipe. This is going to be added in January of next year, is, I believe, the plan. I mentioned LCRD is out there right now. And then finally, on the deep space side, there's a mission going to Psyche. Has anyone heard of Psyche before? The metal asteroid. Very good. I'm glad. Phenomenal mission, phenomenal destination. Learn about it if you're not familiar with Psyche. We'll use a communications payload. So this is farther out beyond Mars. And we'll be able to basically pull up to what would be the molten core of what would have been a planet, but solidified. So I'll kind of end here and just say it's amazing to me even still today, back towards Apollo. I wasn't there for the time, but this video of stepping off the ladder to the moon was actually viewed by over 93% of Americans. I'm not sure 93% of Americans had televisions back then. So people found a place to go to watch this. And this was live, so to speak. Of course, the time delay and everything, and analog. And they used the Canberra tracking station to telemeter it. We can't do that right now beyond the moon. RF is not good enough. As you can see, as we left with Apollo 17, the cameras got a lot better, and the comm got a little bit better as well. But going out to Mars, and of course beyond, this is where laser's going to shine. When we get the first human footprints on another planet, and when we return to the moon, we will be able to get HD video back because of the laser communication system. And probably we'll separate that out and use some RF and C in the laser for the high rate stuff. And so I want to end on talking about helping us with this, because we need a lot of help. There are a lot of challenges, and we're trying to solve them. A lot of the technologies that I shared with you tonight were put together with collaborations with small businesses as well as universities. The formal name for those agreements are SBIRs and STTRs. In my area, in space communications, these are the particular calls that go out. And so these calls tell you, here's a bunch of problems we're trying to solve. Can you help? You write a proposal, and we start working together. Internships. So we have an amazingly strong intern program, and it's amazing to me we've been able to maintain it through the pandemic. In my area at Glenn, we typically get about 40 or 50 interns, all the way down to the high school level. High school undergraduate, which is the undergraduate student research program, or graduate, which, as you can imagine, is the graduate student research program. It's basically like a job board. We write some tasks. I need help doing this, and you respond, and normally come onto the center and help do it. But like I said, this summer we're going to be doing it virtually time. But there's one gateway for that, intern.nasa.gov. So I wanted to mention there's 10 NASA centers around the country, 10 field centers, and then 11 if you count headquarters in DC. One thing you can take advantage of because of the pandemic is you could do a virtual internship anywhere. If you are restricted to travel, put in at all of the centers, because likely they'll be virtual, this year. If you can travel, and they are in person, by all means, that's great. I miss being with the students very, very much. But if you can apply to as many centers as possible, then you've greatly increased your chances of selection. Right before I put this presentation together, they announced an upcoming seminar on how to apply. It's like a 2-hour seminar giving you some hints and some tricks, and it's coming up in February. So if you're interested in an internship, I recommend that you apply. If you're interested, my 2 cents is never feel fearful that you're not qualified for a job. I'll tell you that myself and how I select interns, and I believe I'm being fairly fair with my colleagues. We know you don't know how to do exactly what we're asking you to do. We don't know either. That's why we're asking, right? What's more important to me is that you're interested in learning how to help solve the problem. I will do that. Other people will do that. We'll take the time. We'll give you the tools that you need. So write your response. Do a little research on it. Express how you're interested in it. And I think that'll go a long way towards helpful, successful selection in that. At least it would from me or anyone in the group. And I'm happy to talk to anybody afterward about that if I can share any tips or tricks for you. Hopefully I'll see some of you, at least virtually this summer. And that's everything I had for you. If you're interested in learning more about SpaceCom, we have a newer website you can check out. This is live, the Deep Space Network. If you just type in DSN Live and go there, it'll show you every antenna and who we're talking to at that very moment. And if you don't know all the acronyms, Horizons, you just click on it, it tells you it's New Horizons, and it'll tell you the frequency, it'll tell you the bandwidth, time delay. Right now, it'll tell you the weather in Goldstone. Really cool thing. So in fact, there's Mars Odyssey right there because I clicked on MRO right there. Okay, thank you so much for your time. Any questions I can help ask? I went a little long here. I apologize.
Okay, let's thank our speaker.
Thank you.
Thank you so much for this fascinating talk. So we have time for a few questions.
Thanks for the wonderful talk here. When I was working on the DTM project, one of the challenges we encountered is how to provide the multicasting based on the unicast communication. I guess.
Oh, multicast. Mm-hmm.
Most of the situation you mentioned in the talk is more like unicast. So I don't know whether the product RC covers the multicasting scenarios or not. I didn't thought of that obviously, but.
Great question. So DTN, multicast versus unicast. Here's the scenario, and we are working on that, and here's a typical scenario. At Mars right now, we have multiple orbiters, and I didn't mention they can't talk to each other, or very little. That would be more fair to say. It wasn't put together as an integrated architecture, more of an. In the future, what you'd want to do is a telescope or an RF antenna, because DTN doesn't matter, at the planet of interest, Mars maybe, and multicast out the message in that general vicinity. You don't know who's all going to get it, but they will figure it out. That kind of begs the question of custody transfer. How you do that in deep space and how you do that in near Earth will be very different, again, because of the control feedback channel and the delay included with that. It's much easier to do, I think, in a lunar environment where we're talking about a second or a few fractions of a second going from element to element. But we are still interested in multicast. But I think the end solution will be different depending upon the particular environment that we're in. What you see in multicast on Mars will be different than what you'd see in a near Earth or a lunar environment, because one solution is not going to span that variability of time delay to truly do custody transfer and receipt and acknowledgement. It's still complicated. I don't know if that completely answers your question, but yes, it's still there. Yes, it's still complicated, but we think we have our arms wrapped around it, at least in those two domains. Yeah, great question. Thank you.
Other questions?
Do you and NASA have concerns about the increased number of satellites around Earth and monitoring potential collisions and just other particles?
Yes. Absolutely, yeah. So we have to, it's not unilaterally on us. We work with the Air Force on this, trying to detect space debris. And basically anything larger than, and I apologize, I think it's around an M3 bolt size, we have to categorize and track. We do have this problem from space debris. We also have this problem from intentional space debris. We've already had several international incidents of displays of power, right? We've also had several accidents. There was a Russian satellite that hit an Inmar satellite by accident. And so that locks out those two bands for years, because every time that mess comes back around the planet, it interlaces with each other, and it's like a cheese grater effect, right? We have to track all that. The windshield of the space shuttle was replaced tens of times over its operational lifetime because of all the debris that we would hit, on ascent. It is a big problem. All we're doing right now is tracking it and trying to plan for it. About once a month, we have to do an ISS burn activity because we saw the debris coming within that orbit. We imagine an imaginary pizza box-shaped element around the space station. Anytime we see a piece of debris enter that zone, we do a burn to get away from it. So unfortunately, it's more a see and avoid right now. It's a reactive solution. What I would love to see, and there has been several in the SBIRs, but more like major announcements. We have had some announcements out there for people coming up with ideas of how to mitigate the space debris. So getting up there and tagging it, the larger pieces with like RFIDs, and then ways of moving it around. Probably the best things that I've seen have been some of the ablative things, using high power RF, high power lasers, lighting them up and motivating them over in one direction or another by doing some ablation on one side, or even just the photonic pressure. It actually doesn't take as much as I thought it would to start to deorbit some of this stuff. You don't have to completely move it, you just have to get it on a deorbiting trajectory. So there are a lot of physicists looking at that. What we need is more engineers looking at that, putting together fieldable technology demonstrations and solutions.
In addition to that, how are we designing, new satellites to deorbit when they become unstable or unsustainable?
There's a cultural change going on right now for the better. So, and I'm really happy to see this. I think you're going to see a lot smaller satellites, which are also going to have much shorter lifespans. Things like Voyager 1 and 2 were crowning achievements of humanity to put something out there that survives over 35 years. But the time for that is probably past, because nowadays you would do that mission with perhaps several small satellites flying in formation, much cheaper. A lot of scaling. If you're going to build one thing, you build a few, everything gets a little cheaper, and maybe, oh, by the way, they look kind of similar to these other satellites on this completely orthogonal mission. So not having stuff out there for so long, if you're an Earth observation mission, and Elon's constellation is a prime example of that. Just replenishment, just fly a bunch of stuff. It's all in an orbit that's not going to last very long, so it is all kind of coming back in, but it's small enough that it burns up, and it doesn't cost much, so you don't mind when it does. You just launch another one, and oh, by the way, because you know it's only going to be up there for a short duration of time, you can use the latest, greatest technology on board that isn't proven, because if it fails, satellite's coming down in a year anyways. We'll launch another one. So that's a much more agile way of satellite design. So what I've seen on the NASA side is definitely looking at planetary orbiters for other planets using literally CubeSats sometimes, but at least small sats, and not these ginormous, Lockheed Martin, Northrop Grumman buses that once they're defunct are out there and decaying for many, many decades to come. So although disposability sounds kind of bad, I think in this case, it's a very good thing. Think more about a disposable satellite than something that's going to be out there forever because of the problem we're creating.
All right, thank you.
Thank you for your speech. A couple of years ago, I saw a demonstration about the light eye at takeoff. So, in your opinion, how do you relate light eye? Light eye is obviously in the indoor environment and goes in deep space.
Yes, yes.
So, how do you differentiate between these two? And
Yes.
also, on a similar note, in the near future, how do you relate visible light communication, both in terms of indoor communication, or also in deep field communication?
Okay, great question. Thank you. Okay, so the question was about, the first part was about Li-Fi. Everyone's heard of Wi-Fi. Li-Fi would be light, right? So one thing that we've been looking at is intra-cabin communication. So the space station did re-upped until 2030 by Congress, and nobody knows about it because they did it December 31st, the worst day of the year to apply funding and announce it. A lot of people I work with don't even know that. But so in short, we're looking at, okay, inside the cabin of a space station, ours, the next space station, or when doing spacewalks around the vicinity of the space station, that's where a Li-Fi activity would really be nice, because you could have a high definition camera here looking at the job, looking at the tool set. Any problems, you've got some eyes inside the cabin or on the ground seeing what the astronaut sees, but a live feed of that. And that's, you know, because it's non-directional, as you're moving about, floating about, whatever your task is, it's really nice. So in short, proximity operations is where you'd see Li-Fi.
I'm sorry to interrupt you. There is a class at 2:30. We can
Oh,
have
okay.
this discussion afterwards. Okay, offline. Let's thank
My
the speaker
pleasure.
again. Thank you so much.
Thank you for your question. Appreciate it.
Sorry for that. So,
Oh, no problem.
yeah, this already came in. So.